Welcome to the April 2024 GoldSim webinar. We're going to be talking today about hydraulic simulation in GoldSim and a very specific part of that, which is um, essentially the Bernoulli's energy equation, applying it. Um, but that's kind of deeper in the weeds. The big picture is that what we're trying to simulate is in GoldSim is a pump, and we need to sometimes, as we'll see, we need to account for the losses in the system downstream of the pump station. So the reason I'm bringing this up is because before I worked at GoldSim, I was a consultant um, for a firm we were doing models mainly in the municipal sector for water studies, water supply, water demand studies. And so often reservoirs were involved. And even though we had a really large time step of one day, most of the time, um, we were trying to calculate um, the flow in the system based on a operating curve, a pump curve that is associated with the specific pump that they perhaps had installed. So um, in order to do this, well, we have some options and I'll go through them, but sometimes you can't ignore losses. Um, or you could, but it would perhaps oversimplify some things. And anyway, there were reasons why we needed to calculate flow and head, including losses. And it's a little bit more involved problem. So I wanted to bring this up and how you can easily solve it now in GoldSim. Is that would have been nice back in the day when I was using this, because I was really struggling with it back then. Um, and so that's why I wanted to talk about this. It doesn't always happen. So in this model that I'll show you right now, um, we can ignore, or not, we can't. We are ignoring um, losses here. And so, let's say you have a table that's given to you that's associated with this pump that you're trying to model. And in this model, we have a pond. It's really simple. We have a pond, and then we have a pump. It's pretty much the whole model. And there's a pump that's it's going to pump water into this pond. And what we're going to do is since we're ignoring um, losses due to pipe friction and so forth, because of that, we can just say, well, the head and flow relationship that we are given for this constant speed pump. Sorry, I should need to back up a little bit here. I forgot to mention that we're talking about constant speed pumps here. Okay, so just so that's known. All right, so we can calculate a static head, from the pond where we're pumping water into, um, that difference of elevation and our suction head of the pump, let's say, which in this case, in this simple model, we're just assuming is datum at the pump is 0. So that's the starting point. So delta Z is just whatever head we calculate at the pond, assuming that the bottom of the pond is the same elevation as the pump. But anyway, obviously in a real problem, you'd have a little bit more going on here, but just trying to keep things simple. So this head then is used in a lookup table. So here's a lookup table. It's called head flow table. And this is something that you might be given from, the manufacturer of the pump, right? So they would have this in their book, and it might have more points than this. Now, GoldSim is interpolating linearly between these points, so just keep that in mind. If you have a curved line, you'd want more points in here. But depending on the head that we calculate, which is just a water level, that's it. Then we can associate a particular flow with that. So in cases where we can ignore losses, then this could work pretty well. Oh, somebody said it looks like there's a new version. Yeah, so a new version of GoldSim. This is a beta test environment, so This is not released yet, but this is what it will look like when it does. Well, maybe there's actually going to be a new element, which is what we're working on right now. So we're all pretty busy with it actually. But this is what it will look like. So we're, and you see there's a new icon and stuff. So, but it's, we've had to do quite a bit of work to get it ready for a lot of higher resolution screens. It's quite a bit of work actually to do that, because the zoom scales can be so much greater. But anyway, so we have this head flow table and we just define it with a one-dimensional lookup table, right? So then all we need to do is just say, okay, tell me the head and I'll tell you the flow. Very simple, just a very immediate calculation, very straightforward. Okay, so then what happens is, well, we're running our model and we get weird things starting to happen. So in this case, if losses are significant, okay, so here's a model where I'm doing the same thing. I'm pumping water through this pipeline into this tank, and down here is a plot over time. And so what I'm going to show you here is this bottom chart down here. So there's a lot going on. So let me just explain it here. So we've got red is the water level, blue is the pumped inflow. And you'll see there's a dashed line and a solid line. So the dashed line is doing what I was telling you, is ignoring, it's actually not ignoring head losses. It's assuming a constant head loss. And that's one thing you could do. You could say on average, on a daily average, it's just too complicated. We just want to assume that there's just like this extra loss, a factor that we're going to apply so we can calculate the flow. And also I should say, by the way, the reason we were going down this path and getting into this kind of detail is because at the start of the project, someone would say, we have this pump here and the project is to potentially replace it with a bigger one, and here's this new pump curve for the bigger one. Can you incorporate this in the model? And so this is another reason why it became important to us also, that they were trying to calculate the cost of pumping, the energy cost. So we want it to be pretty accurate as far as how much energy we're exerting, and we just needed that. Even though losses might have been a somewhat minor component, we still needed that to get a more accurate model. So that's again the reason why we started to try to do it this way. But what I'm trying to show here is a difference. What's the difference between solving for it more accurately versus just using that lookup table I showed you, where you ignore the losses? And so what happens is, one of the consequences, what I started finding, is that with an estimate, you oftentimes will fall short, or you won't be accurate necessarily all the time. You could be close, and if you look at the flows are actually pretty close together. These blue lines, they're both maintaining this water level pretty well. And there's another line here. I don't know why it's the same color. That was a bad idea. But it's it looks like another red line, but it's just the straight line. That's the target we're trying to maintain. So you can see that both of the pumps, whether we use a solver or just a simple method, it's similar. But you see that the dashed line of the red line, it's showing the tank level is really low all the time. It's undershooting. It's not able to get the tank level up enough. And so in a simple model, one thing you could do is just adjust for that by raising the target. You could do a number of things and probably come up with a model that is close enough to what you're trying to do, with avoiding doing this more complicated pump regime in the model. So in a case like this, it would probably be quite helpful to put the solver in there, because then it would more mimic what reality is. Even though you're using maybe a larger time step, that might, I guess, kind of in itself just kind of lump together a bunch of things that might happen during the day, like a pump turning on and off multiple times. So you're looking at average daily flows. But for larger systems, this does become quite important. And so you can see there is a difference here. And we would have to further contrive the model, if we wanted to continue down the path of estimating the pump flow. We'd have to further contrive it to get the water levels to be where, historically they might have been. So anyway, I just wanted to bring this up because sometimes you look at a plot, and maybe if numbers look low for some reason, you might think a totally different thing. It could be, oh, maybe my losses are too, or maybe my demands are too high. I'm pulling too much water out of the tank. You can come to conclusions that aren't reality, right? So obviously that's why an accurate model is more important. Okay, so let's talk about how to do this. And we have an example on our website called Pumped Head, I think, and I can point it to you. And we're also including this. We'll have links to this in our archive along with the video recording of this. Okay, so here's a really simple model where, once again, we have a pump and it's delivering water through a pipeline up to some tank. And I've drawn these dashed lines over here to kind of represent the different components of the head component. So we have the DZ, that's delta Z. So typically, like textbook style, you have Z1 here and Z2 over here, meaning the elevations. So the difference between those, the static level differences, and this dashed line, moves, right, depending on the water level in the tank, right? So that's kind of dynamic through time, but not a big deal. It's easy to track. You just can use geometry if it's a tank, or a lookup table if it's a pond. So that's going up and down, and then this additional component is what we're after. Okay, so I'm going into this container, and what we have here are two methods. We have the simple estimate, which I was talking about earlier, with one additional thing, and that is an estimated head loss, just as a static number. So if you go into the simple estimate, then we're using this pump curve still, but we have this, I'll call it HF gas. This is friction head loss. I mean, it's supposed to include all losses, minor losses too. So maybe HF is the wrong term, but anyway, so I just put in a number here. That's just, just what we think it might be on a daily average, for example. So with that known, now that that's known, now the problem's really easy. We can simply calculate the, we add that friction to the difference in the Z, delta Z, and then we can calculate flow from the lookup table automatically. Very straightforward. Power calculations in GoldSim are very simple. There's an efficiency curve shown on that original page. I'll go back to it, but you'll also have an efficiency curve associated with the pump. And so then you can say, well, based on the flow that we're looking at, this is going to ultimately be the efficiency that it will be running. And then we just put that into the horsepower equation, which is just this part I highlighted right here. So that's H times Q times specific gravity of water divided by the pump efficiency. So because we're dividing by pump efficiency, you can't have a zero down there. So to avoid a divide by zero, I have this if statement. So that's not really something to worry about too much. Okay, so power calculations are really simple, but it all comes down to this guess value you put for the head loss. Okay, so sometimes we can't do that. We don't want to do that. So here's a script element, and this is in that model example, but I wanted to just run through it so that you understand what's going on here. We're using a solver, and the reason is because we don't know flow and we don't know head yet, right? So we're going to use, in this case, a binary search algorithm. It's just a fast way to converge onto a solution just by iterating. And you'll see, I'll show you. I won't go through all the detail. I mean, you can look it up in a textbook, but essentially we put in all of our definitions, information about the pipe, and then we calculate some of these static things can be calculated. Anyway, we're initializing a bunch of stuff, and we get down to here. And so this is the important part, is that what this solver does is it says, let's start with a guess, a high and a low guess, and we know we're going to be in between there somewhere. We're trying to calculate the flow that we're pumping through this thing, and we don't know what it is, but we know it's going to be somewhere between 0 and a billion cubic meters per second, some really big number, right? Ridiculously high. So we know we're going to be somewhere in there. That's where our answer is. I also set up a thing called converge, so that when we become converged, it drops out of our looping. And by the way, in a script element, you're able to construct looping functions, like a while loop or for loop or something, and what it executes every time all the other elements update in the model. So that means for example, at every time step, this script will run every time, unless you put some if statement that tells it not to, which we do right here on line 30. We say, if the pump is on, then proceed forward. The reason we do this is because we also manually control the pump, whether it's a human doing it or an automated process. Usually a pump will be shut off because of some reason, like a water level in the tank being too high or something like that. And so that's exactly what we have in here. And that's a very common thing, right, in GoldSim, to have some sort of controller that is controlling it. But once we know that the pump is operating and on, then we go jump into this while loop. And so we start with the first guess that we put in. We know we're between these two big and low numbers. Let's just divide them and say this is now the midpoint, and we add it to the bottom one. So it actually puts us right into the middle. So that's why we call it mid. So that's our first guess, a really big number. And then we get down here and we say, okay, let's just go ahead and just calculate our losses. Let's calculate our head losses. Since now we have the flow, now we can calculate it. And I'm just using the empirical head loss formula called the Hazen-Williams formula. Maybe if you wanted to be a little bit more accurate, you could use the Darcy-Weisbach, but I don't have it in here. I do have another example if you could go look at it, and you'd have to replace it in here, but it wouldn't be too hard. Anyway, we calculate these head losses. Now we're able to calculate the true total dynamic head with the losses. And so now that we have that, we can now calculate what the flow is, and that's the result of this thing. Also, if you don't like saying that, if this thing is called discharge script and you wanted to refer to the flow, you have to say discharge script. That's kind of weird. So you could add another, just like I did right here at the very bottom. I added a new internal definition Q, and I exposed the output, and I just called it result. Or just assigned it to the result. So that way, if you want to refer to the flow out here in an equation, then you could say discharge script dot Q, but that actually is the same thing as saying discharge script. So anyway, different ways of doing things. But anyway, so we get down in here, we calculate the total dynamic head, we're able to calculate the flow, and then this is the important part, this next part. This is the whole point. This is the kind of the main part of this type of solver, is what we do is we evaluate the result and we say, okay, is that greater than or less than the midpoint, our guess? How does that compare to our guess? And if it's less than our guess, then we reassign the high, we move it down, and we're like, oh, we're less than the guess. Okay, that means that our new guess space, the space of our next guess, should be the bottom half, right, of our original space. So we zeroed in to our correct answer pretty quickly, just by making this adjustment here or here, depending on if we're above or below our guess. And then we kind of test here and we say, is the difference between the high and, because essentially you're closing in on it, right? You're closing in on the right answer by subtracting the high and the low guess after you do that reassignment. And so you're essentially, you can imagine it in time, not in time, sorry, in number of loops of this iteration, I guess, over computer time. It's the the high and the low are kind of moving up and down, but always coming together, always not moving up and down. They're either not moving or they're moving closer together, right? And essentially it converges onto the solution. And we have built into here a number, but you could give this any number you want here to say if it converges. But once that's done, then it exits out. One more thing we could do in here on the convergence is we could say, sometimes something goes wrong, there's a bug or something, and you end up never converging. So we'd want to avoid that for sure. What I would say probably you'd want to add in here, just if I was sending this to the customer or something, I would probably put in some safeguards to prevent yourself from getting into or from an end user that maybe uses weird numbers in the inputs or something, just to avoid the situation where you could start iterating forever and then the model just hangs, because it would just be sitting in this loop forever. So I would say put a counter in here, right? And every time this loops, you count, and then say converged if this, or counter greater than, a big number. But I don't think we ever iterate more than 100 times in this model. And as you can see, it's not too slow. So let's see, I just hit run and it took less than a second. But I mean, we're only running this for, this is a static model. But if you want to see how it runs in like something that's got a lot more calculations, let's see how it goes. Calendar, and then let's say we just want to do it for a lot of days. And then I need to put in 1 day time steps. Okay. See how that goes. Okay. So it ran for about 25 years, 1 day time steps, and in about 1 second. So it's not too bad. But it is definitely going to be slower than your simple lookup table. I'm just doing static because I just want to show the difference once again between the simple and the script calculator. So on the left is the simple lookup table, and on the right is this discharge script. So the discharge that we estimated for the simple one is quite a bit higher, and total dynamic head is less. And now I've put in this model on purpose a very large loss factor, essentially a very small pipe, small diameter pipe, on purpose to show that there's a big difference here. But what that does is that puts you into a totally different category on where your horsepower calculation would be. And that might be the important part of the whole project, is to find out how much does this cost, to operate this system. And so, as you can see, it would be important to have that in there. Okay, so I didn't really talk about the efficiency curve, but this is a type of a curve that you might see. I mean, there might be actually more things on here than just these 2 lines, right? But this shows total dynamic head in blue and efficiency in the gold color. And they're sharing the y-axis, so you kind of have to just think about it that way. I couldn't actually figure out how to get the efficiency over on the other axis in Excel. But anyway, what you see here is that because the efficiency curve curves up and then down, you could get the same efficiency for 2 totally different flow rates, which just by coincidence that happened to me here. So, whoops, I was showing them this way. I don't want to be confusing to everybody. So, okay, so the estimate gave us 3,000 GPM, and the script element gave us about, let's say, about 1200, a lot less. But it turns out that those 2 points just coincided almost on the same horizontal plane. So the pump efficiency in both cases says 65. At first that stunned me. Then I realized we were just on different sides of that curve, which is interesting. But anyway, some of these things to kind of consider. But I hope this is useful. I realize that there's uh, there's a lot of details here, and it probably would be best to play with the model yourself, download it, and then play with it. So one thing I was thinking of doing that I didn't do in the previous webinar session was show how this actually gets implemented into a real model. What would you do? And there are some things that come up when you do it. But at the same time, I realize that can get I have to go out on a limb here, because sometimes I end up doing something that, I didn't rehearse ahead of time. So bear with me. I hope I don't run into any problems. But before I go into that, are there any questions so far about the script element? Anything you wanted to cover again on that? It looks like we're okay. All right. So what I want to do is, let's say we want to use this this model that we're looking at right now, and we want to incorporate it in our model, which just so happens to be pumping water into a tank. So we can say, okay, let's do it. Let's just take, I guess, this, those elements and this, and I guess we could take this. And we'll just copy all of this right here. And we'll start a new model. Oh, do I need to save this? Yeah, sure, I'll save this. Okay, new model, and okay, here we go. So what we want to do is we want to see how much it would cost to deliver water into this tank that has a little bit of demand, and maybe the demand is uncertain and it's going up and down. So we'll put a stochastic in there for the demand that's drawing water out. But we want to see how much it's going to cost, let's say, to run this for 2 years or so. Okay, so first thing is we'll say, yep, let's look at the duration of time. We'll start today and we'll have it run for 2 years. And it's a 1-day time step. Okay, so we got that part done. And then I just wanted to run the model because I forgot, or I need to know what the flow rate is approximately. Oh yeah, 1200 GPM. Okay, so let's say we have a demand that's maybe averaging on that, I guess. We'll see how that works. So this is our demand for water to come out of the tank. And just so we keep it simple, we'll say 1200. Maybe let's just say 1000. I think that's okay. Something like that. And then I'm just going to randomize it through time, because that will make it a little bit more interesting. So every day we're going to resample, but I also want it to be autocorrelated. Now, in reality, you would have some sort of time series here, but we can have a look to see what that looks like, what I just built. So this is our demand on the tank over time. Okay, so then we need a tank. We need to define the tank. So let's do that with a diameter. I guess we should. Okay. I think what we need is a tank container. Hopefully I haven't used that word yet. And then I'm also going to localize it. And I want to localize these because we might be referring to things like diameter, in both places. I don't know about the pump station, but that's okay. Usually when you're modeling a system, and you're trying to represent actual physical components like this, then I would localize them. It always pays off in the end because often properties of those things have the same names. And anyway, just that alone would be a reason to do it. But also on the outside, when you're working with these things, you can easily refer to the object name, which is great. Okay, so we have a diameter of the tank, and I think that's probably all we need right now. So from here, then, well, we don't even have to do that in here. I think we can, well, let's see where we go. We're trying to, um, in here, we're trying to keep track of the water level over time, and we're trying to keep track of the volume. Okay, so we're going to need a pool, and we're working with gallons per minute. So I guess that means we need 1,000,000 gallons, and I don't remember if we have 1,000,000 gallons in our units database. It looks like we don't. Um, so why don't we create one? So we go up here to model units and then add, and then I usually use a large M for million. This is just a description, a text description. And it's 1,000,000 gallons. Make sure I put 6 zeros. Yeah, okay. Volume, yes. And so now you see in our volume category of our units database, we now have an MGAL there. Okay, so 1,000,000 gallons. And then the flows we're calculating, we always report them in GPM. So that would make it easy. Okay, so that's our volume. So now to calculate water level, we're going to need the area of the water surface. Oh, we're using English units, so feet squared, I guess. It doesn't really matter as long as it's an area. So we have diameter times pi divided by 4, but I missed something, didn't I? Diameter squared times pi. What did I do? Oh, I forgot to put dimensions on diameter. So let's say it's what do we say for now? Maybe 300 feet. And then now we can calculate the area. Now we can calculate the depth. Okay, we'll get there. Depth, feet, and then volume, or pool 1 is the volume, and then we divide that by the area. I think that should be correct, right? Correct me if I'm wrong. Hopefully that's all good. Okay, so we're calculating the depth as we go along. And so then what we want to do is we want to say, okay, if we're below that depth, then we want to pump water in. So this is a different type, this is a whole different subject. I've talked about this in other webinars, but this is where we want to put a controller in here to say we're going to control the pump station or turn the pump on when this depth drops below a target. So we need a target. So we're going to put the target in, but what we really want to do is put the target over here at the pump station because that's where the controller is going. So we'll go in here and we'll say we have a target. This is the target tank level, and let's say the target is I don't know, 10 feet or maybe 20. I just have no idea the magnitude of these numbers right now. And that's always the problem with setting up a pretend model. So anyway, that's the target we're trying to meet. So that means over here we need to refer to what's the current measured tank level. This is what we're monitoring, and we have to bring that over from that other location. So now we just brought it in. You can see that the input port has a dot there. Okay, so here's something this is what makes models to look complicated, right? Because we're sending information around this model, but we're trying to represent a flow is what we're trying to get to. We still haven't gotten there yet, but I'm just sending information from the tank over to the pump so it knows, hey, I'm monitoring, whatever you're doing right now, so I can turn a pump on and off. And a really good way to control flow like this, well, I should start over. A really simple way is using a status. So what we can do in here is we can say if and I'll just say on true for now, if the tank level drops below the target, then we're going to turn it on. Then the pump gets turned on. We're going to turn it. Oh, I already have one. Oh, yeah, yeah. I'm going to replace that. So this is what we're doing is we're replacing this thing, that pump on. Okay, so now when I hit the F9 key, you can see here that our controller is now controlling the pump. And I'm not going to do an estimate here. Okay, so now we're controlling this pump just as we were before, but now we're doing it dynamically through time. And I'm going to turn the pump off when something becomes true, when tank level is above the target. You also want to add a deadband usually. We want to give a little bit of leeway, so we could say we're going to let it drop down. It's okay if it drops down. So we'll just say multiply by 0.5. So that means it has to drop down pretty low before we turn it on. But when we turn it on, it'll stay on until it gets way up there just to top it off. Something like that. So that's pretty common way to turn a pump on and off. And then we have the discharge script hasn't changed. Power calculations haven't changed, but the pipe, we can just assume now the pipe is the same for now. Which, by the way, how long is the pipe? 500 feet, and it has a diameter of 6 inches. Okay. So another thing we should do every time, before you get too far down the road in a model, it's always a good idea to just run it for a short period. It just gets too complicated when you run things for a long time. Okay, so what it should do is it should fill and then stop. That's what we should have seen. And we didn't see it do anything actually. Because, why? Let me see. It says it's on. Because I didn't add the flow. I didn't add the inflow. Okay, so that would do it. So now what I need to do is I'm going to just move some things around here a little. Okay, so I need to add the flow components here, both of these. So I'll do that now. So I'm going here to the inflows to the pool, and then I'll go here to pump station, and then it's discharge. And then on the outflow side, we have the demand. We'll just call this irrigation or something, whatever we're using the water for. And then we'll put that demand there. And it's actually probably just better to put the demand inside because it's not really helping us understand the system by seeing that out there. So I'll just move that in and put this over here. It might be useful to see a line to the delivery point, so we could add another expression out here that says, whatever the resulting flow was, what's delivered from the tank. Okay, so let's see if we can get some water moving. So I'm now plotting the time history of the tank, and you can see it is filling and draining. So that's good. That's what we wanted to see. It's not exactly straight lines because our demand is fluctuating through time. So let's go ahead and add then the inflows and outflows. So the inflows we could get to by looking at the pool because it reports it, the total inflow. But if we just wanted to know what the pump station is doing, then we could go back over to the pump station, get it, but it's going to be the same. So I'll say total inflow, and then I also want to just see the total outflow, which is also reported right here. Okay, so this is what the system looks like. So you can see that our pump flow is quite a bit higher than the demand, so we're able to fill it pretty quickly over time. And let's go look at also our head losses. So in here we can get to the head loss looking at I exposed one of the outputs called TDH, total dynamic head, but I also refer to it right here. So we can look at that plot. So it's showing that it's up here at 60. And I don't know if you recall, but in the previous model I showed you earlier, we were reporting about 40, I think, on the head. But so this is the total dynamic head that we are reporting there, and then that essentially translates to how much power. And so then if we wanted to keep track of the energy, then we could just use an integral and say, depending on what units you want to use, we could go look at some. Let's see. So because we're using, let's see, English units, then, oh, I'm in the wrong. I guess it is. No. Where's, let's see, I'm looking for megawatt hours. There's kilowatt hours. Oh, maybe we just don't have it. Interesting. Okay, I thought we had that built in, so maybe we don't. All right, so let's see. How about I add that megawatt hours. And then this is going to be 1,000 kilowatt hours. There we go. Okay, so then we could put that here. And then we just simply put the horsepower, because that is a rate, in there. And so this would be energy. And then you could start looking at scenarios, or also putting a dollar amount on that over time to see how it operates. So anyway, I just wanted to show you how you could hook this model up, but it's pretty straightforward. It turns out that I kind of just knew, I have a lot of information about the model that I'm assuming, so it makes it really easy. Obviously, in a real world model, it might be more complicated than this. For example, demands might be a function of a whole bunch of other things. So yeah, things can get quite a bit more complicated. As you can see in this model, if we're trying to represent where the water is moving, there's only one arrow that represents water, and it's this one. So you in a real model, you might have a lot more things going on, and so it would be a good idea to try to clean this up a little bit. There's no reason to have Z1 and Z2 sitting out here. That's not really helping us in any way, unless we're trying to put these elements over here next to a diagram or something. But even doing that isn't really helping us very much. So it probably is better just to put them, tuck them away. So anyway, that's the model. Oh yeah, there is one more thing I've seen people do. Sometimes when you're calculating the costs of energy for a pumping station, sometimes it's also important to include, sometimes there's a thing called a demand charge, or a specific type of charge the utility company charges every time you turn on a pump. And so you can easily track those using discrete changes, because those are transactions that occur instantaneously when an event occurs. So you could say, when the pump turns on, and just only at that very moment, then just charge a dollar amount to the total. So that can be easily done with a discrete change element, this thing right here. So you would say add demand charge, and it would be, if we're talking dollars, that's usually how they, I guess, I'm pretty sure that's back when I've done this, that's what we did. And then they charge an amount every time you turn it on, and you would say add, and then you would say trigger, and then just say on true, pump on. And then that triggers that $1,000, and then you would add that to either just an integrator keeping track of total dollars, or you could even go as far as using the financial module, and you could say add that into my cash flow over time. All right, so that concludes the presentation. And I just wanted to mention a couple other things about next month. We'll be hearing from a guest speaker about Muck 3D and how it can be incorporated with GoldSim. And so head over to our customer care learning resources, go to webinars, and you will see our lineup here. So I think this would be a really interesting presentation. I don't have actually any experience with Muck 3D, so I'm definitely interested in seeing how this works. But I'm pretty excited to see what Simon has to present there. Also, if you have any other suggestions or ideas about what you've been wanting to see, or you and your colleagues have been wanting to see, please do let us know. And thanks again for joining us, and hopefully we'll see you next month. Also, don't forget to register for our user conference coming up in September. Thanks again, and let me know if you have any questions.